Howdy. I wanted to take a closer look at part C of today's quiz question. This question was 2012, number 2. And you're given a region R, and in part A you're asked to find the area of R. In part B you're asked to find the volume of a solid whose bases are. And now in part C you are asked to write an equation that will find the value of k that is described in this way. The horizontal line y equals k divides R into two regions of equal area. Write but do not solve an equation involving one or more integrals whose solution gives the value of k. I wanted to look at this question because many of you tried some different approaches on this, and some were successful and some were not. First of all, let's understand the question. The horizontal line y equals k divides R into two regions of equal area. If I draw myself a horizontal line and label that y equals k, I get a sense of what's going on here. And what I'm told is that if this is R1 and this is R2, that the area of R1 is going to be equal to the area of R2. And so there are several different ways that I could successfully set this up, but all of them revolve around the same idea. And that is that if I take this area right here, it will then be equal to this area right here. And so we can express that really in one of three different ways. First of all, we could take that very literally, and we could compute the area of R1. And the area of R1 is best done with horizontal rectangles of height dy, whose width is right curve minus left curve, so that the area of R1 would be equal to the integral from the lowest y to the highest y of a right curve, that would be x equals 5 minus y, minus the left curve, which is x equals e to the y. dy. So that's the area of region R1. What I could do then is to directly set that equal to the area of R2, which will be the integral from k up to the top intersection point that we saw in class. We just labeled that point B of the right curve minus left curve. So this is one way that we could write an equation to find the value of k. The other way is to recognize that both the area of R1 and the area of R2 will be exactly half the area that we found in part A. So if we call that area A, then I can set A over 2 equal to the area of region R1, just like that. And this is probably the most efficient way to set it up. Now, I did have students try a couple of other things, and I want to talk about those things and why they don't quite work out. I had several students who saw this horizontal line and thought, my goodness, that looks a lot like an average value. So I had people who tried to make k, y equals k, be the average value of my function here. And so then they dutifully found the average value of a function that was y equals ln(x) up to point A, and then 5 minus x thereafter. And the problem with that is that the average value is not exactly right, and here's why. The average value is going to give me a rectangle whose area is exactly equal to the area under the curve. So if this were f average, let me draw f average at a different place so we're not confusing ourselves. Put f average right there. Put it right there, just like that. So our f average is going to give us the height of a rectangle whose area is equal to the area under the curve. So that means that this area right here is equal to the entire integral, like so. And we express that as f average equals 1 over b minus a, integral from a to b of f of x dx. Or in other words, equating areas, f average times b minus a equals the integral from a to b of f of x dx. And if you take a look at the curve that we have right here, let's identify 3 regions. Here's one, A1, there's another one, 2, there's another one, A3, and then actually let's identify a 4th region up here, A4. The integral from a to b of f of x dx is going to give us areas A2 or A4. And f average times b minus a is going to give us the area under the rectangle, which is equal to A1 plus A2 plus A3. And so when you cancel A2's from both sides, what you find is that A4 equals A1 plus A2. Or another way of putting this is that A1 and A2 right here are going to be equal to this guy right here, and sadly, they are not going to be equal to the area A2. So that didn't work. I had some other people try to do an integral kind of like this. They had, let's see, 0 equals the integral from 0 to a of ln x minus k dx plus the integral from a to 5 of 5 minus x minus k dx. And unfortunately, this approach right here also fails to compute the right thing, because the way I drew it out here, if this is the line y equals k, then the integral from 0 to a of ln x minus k, there, is going to compute all of the net signed area here and here. And the integral from a to 5 of 5 minus x minus k is going to compute all the net signed area from there to there. And if I set that equal to 0, then I find that, lo and behold, I inadvertently computed the average value. So the k that you find right here is actually just f average, which, as it turns out, is not the same as the k that we're looking for. So I hope this was helpful to you. Again, the right way to do this is to find the area of the region and set half of that area equal to the integral from 0 to k of right curve minus left curve. Because what that does for us is to compute the area of this region right here